Okay, here's another critical velocity equation. This one's a little more interesting, I think. Draw an FBD of a satellite orbiting the Earth and derive an equation for its orbital velocity. How fast would something have to be going around the Earth at a particular distance from the Earth at a particular orbit? So we can draw the Earth. We'll draw the Earth here, and then here's an object, and it's going around in orbit. Okay, and I need to draw an FBD for this. So this is a pretty easy FBD to draw. There's only one force. The Earth is pulling down on it, right, with mg. Okay, that's the only force. There's no normal force. There's no surface it's riding on or whatever. There's just the Earth pulling down on it. That's providing the centripetal force to make it go around. And so we can just start really easy. F net equals mg. And of course, F net is centripetal force. So it's not just ma, it's mv squared over r equaling mg. And the masses cancel. And again, we get the square root of g times r. That's exactly like it was going across the top of a loop. Now, this one is a little more difficult than this, because if you're going around the top of a loop on a roller coaster, gravity is always 9.81, because any roller coaster is on the surface of the Earth, so gravity is 9.81. But what's gravity here? So, for instance, if you just look at this equation and you say, well, what would happen to the critical velocity? What would be the orbital velocity? I'm going to call this orbital velocity. What would it'd be a different orbital velocity, right? If it was further out here in a higher orbit. Okay, if it's in a higher orbit, should the velocity be more or less than what it is right here? And if you look at this equation, you would think, well, I think it'd probably be more, because the r is bigger, right? The radius is now all the way out to here. So if the r goes up, the orbital velocity should also go up, right? Well, that's the deceiving thing, because what about the gravity? See, the gravity is not 9.81. The gravity is whatever the gravitational field is right out here at this point. But if I go up a higher orbit, now what's happened to the gravitational field? Well, actually, it's gone down, right? We already know this from earlier units, that the gravity gets less the farther you get away from the planet. So this gravity is going to go down when the r goes up. So what happens to the orbital velocity? Well, if the r goes up at the same rate the gravity goes down, then the orbital velocity actually stay the same. But we know that gravity is an inverse square law. So as your radius goes up, your gravity actually drops off faster. And so the actual velocity, orbital velocity out here in a higher orbit is always going to be less. The higher orbit you go, the less the orbital velocity you actually need. That was really even confusing to some astronauts at the very beginning, in the Mercury astronauts, when they figured out that they'd have to speed up to try to get out here farther at a higher orbit. But then once they were in this orbit, they actually had to go slower. They had to slow down than what the velocity they were traveling around in this particular orbit. They were actually going slower out here to maintain that orbit. Because if they go faster than that, they'll actually start going in a higher orbit, or eventually maybe escape the gravity altogether and spin off into space. So this equation is not as simple as just this. We need to actually put in an equation for gravity, because the r isn't just the only thing changing. The gravity will change every time the r changes. We should know, and hopefully we'd remember an equation for the gravitational field. If you remember, the force between any two objects was big G, mass of one of the objects, in this case we'll say the mass of the planet, times the mass of whatever the satellite is, okay, or object maybe. And we divide it by the distance between them squared. We'll call that the radius squared. Now, what is this force? What is this force over here? Well, the force over here was this force right here. Basically, it's the weight of that object, the downwards force that the Earth is pulling on it, which was, m times g, which is the mass of the object, times the gravitational acceleration towards the planet, and that equaled big G, mass of the planet, mass of the object, over radius squared. And of course, remember, the mass of the object always canceled out. So we had an equation for gravitational field was always big G times the mass of the big object pulling on the thing, mass of the planet, and it was divided by the distance squared, or the radius squared from the object was from the planet. So this is going to change, at different radiuses. So we're going to take this gravity, and we're going to put it in for the gravity in this equation. And so what do we get? We're going to get orbital velocity equals the square root of big G, mass of the planet, and then it'd be over the radius squared, but we also have times the radius. So technically it's just over the radius. So here is technically your orbital velocity equation. We can't really leave it like the roller coaster one, square root of Gur. That's simple, but that's a little deceiving because as the radius goes up, the gravity is going to go down. So we want to combine this all together, and if you want to find the orbital velocity of anything orbiting something else, you do square root of big G times the mass of the thing you're orbiting, the planet or whatever you're orbiting, divided by how far above the center of the planet you're orbiting. And you square root that whole thing. So there is an orbital velocity equation. Hopefully you understood that derivation.